Thank you. I'm glad to see you all here. I'm from Minsk. Minsk is a very interesting place for now for computer vision, as we have lots of computer vision startups. And one of the most famous startups is Henet. They built a very good framework for neural networks inference, and they were acquired by Google. And now we have a couple of startups in Minsk. For example, I'm working at Wannabe. We are making augmented reality for e-commerce. We also have One Soil, a startup for farmers' agriculture. They help a lot these people. And we also have department of Mapbox, which is fully in Minsk. They are developing a mobile application to help drivers, and they use neural networks on mobiles like phones. So I'm working as a deep learning engineer. I'm developing for the last year efficient neural networks for semantic segmentation, most of all. And I also have some experience with board microcomputers like Raspberry Pi. So let's start. I came here because I have lots of friends. Some of them are good researchers, but they have very good applications like guns, but they don't have any ideas how to put their big, large networks for production, for example, to mobiles or microcomputers. But I think that it is a very simple topic. It's very simple to make efficient networks that will be have accuracy such as big nets. So I'm going to talk about different convolutional neural networks architectures. It's MobileNet, SqueezeNet, Shiftnet, ShuffleNet, MobileNet version 2, Henet, EECVC. And I'm not going to talk about some hardware hacks or advanced techniques for training networks. And I don't want to talk about exact numbers because when you put everything to production, everything varies. So when you have a task to develop an efficient neural network, you should pass through some steps. At first, I think you should understand your task. For example, you should feel how big a receptive field do you need for your task, or maybe you need you have very different features, so you need to use lots of filters. Then you try to use an efficient known architecture for mobiles, and then when you get the first baseline, you try to improve some learning details. And when you have a very good net, you can put it into production and use such techniques as quantization. And in practice, it really helps even more than tuning architectures. But as many people know, there is no silver bullets, and there is some pitfalls why it is. So, first of all, everything is dependent on the framework you use. And I had some conversations with people who are connected to development of Caffe 2 or some other frameworks, and all they say, in some cases you can build a better network on our framework than on the other, but we can't give you any advices. We have no guidelines what operations are good in our framework and what are bad. Just please send us your neural network, we run and tell you some benchmarks, and that's all. when you try to put your network to production, you always face some problems with conversion from one framework to another. For example, the best way to run neural networks on iOS is CoreML. And the only good version of converter is converting from Keras to CoreML. But if you are developing PyTorch, you can face some problems. And in many cases, in papers you find some good theoretical findings, for example, like MobileNet version 2. But many people in practice say that it's working good only on dataset from paper. And when you are developing a very, very good network, but at some time you realize that the whole pipeline, for example, acquisition of image, is too slow. For example, neural network takes about 15 or 20 milliseconds, but your data acquisition is about 200 milliseconds. So most people in deep learning think that the research was moving to stack more layers and cover yourself with more GPUs. But it's not absolutely easy. So when we look at closely to the history of development of networks, we will find that yes, they try to use all the resources they had, but they try to use it efficiently. For example, when we look at AlexNet, we found that they used ReLU because it was far more efficient than using tangent hyperbolic function. And they also, for performance hack, use group convolutions. And these group convolutions became like a father for the other mobile networks like MobileNet, ShuffleNet. And when we look at VGG, we found that in AlexNet there were big 5x5 kernels, but in VGG all became 3x3 because it was more fast. And the Google Net Inceptions introduced 1x1 convolutions, again because it was an efficient way to compress channels. And also there is some server-side efficient networks that became the predecessor of mobile nets like Exception. So one of the most popular first networks efficient for mobiles and embedded systems was SqueezeNet. And they highly exploited the idea of 1x1 convolutions. So 1x1 convolution has no sliding window, it's just vector by vector multiplication, and it can be implemented very fast. And they had 5 models, and it has 2 parts. The first is squeeze part and the expand part. And first they do just cheap 1x1 convolutions, and they shrink a lot input channels of the tensor, and on the expand they are doing both 1x1 and 3x3 convolutions. And the idea of using 1x1 with 3x3 was to make it cheaper than 3x3, something like this. So, but they, even though it was one of the first good networks, efficient, but they had good results. For example, they had 50 less parameters and very low size. And the next paper I really like, it was developed for semantic segmentations for autonomous driving. But before telling the exact architecture, I need to remember some basic operations like dilated convolution and transposed convolution and asymmetric convolution. So dilated convolution is made by a kernel with some holes. We can call it dilation, and for example, if we take dilated convolution with dilation rate 1, it has a receptive field of 5, but it works like a 3x3 convolution in terms of speed. And what is asymmetric convolution layer? It is decomposition of large kernels by, for example, if we take a 5x5 kernel, we can decompose it to 5x1 convolution and then applying 1x5 convolution. And if we count the operations, we find that it has almost the same number of multiplication add operations like in 3x3, but it has a large receptive field. And when we develop an efficient neural network, you should always keep in mind that we need to grow very fast receptive field of the network. And I think most of us know what is transposed convolution. It's used for semantic segmentation, for super resolution. It helps to increase spatial dimensionality of the tensor. But it's much more efficient as it's learnable as, for example, bilinear interpolation. For example, you can always initialize your transposed convolution with bilinear iterations, bilinear interpolation, so it has all of the same efficient, so they have the same running time, but it can be learnable. So let's take a look at the whole architecture composed from all of this. At first, they had a small input block. They diminish the input resolution by factor 2. And the most interesting part is the blocks. At the first step, so it's ShuffleNet usual block. They perform 1x1 convolution that compresses input channels by a factor of 8. Then they do in convolutions, and they have 1x1 expanding convolution to the initial number of channels. And they also everywhere used preludes. It's parametric ReLU. And the most interesting part is they didn't use ordinary convolutions. They mix in different kinds of convolution. For example, they had usual convolution, dilated with dilation rate 2 convolution, symmetric convolution with 5 kernels, and they all mixing it, and they achieved a really good results from my point of view. It's really good, working good in real time. And they noticed for semantic segmentation tasks that usual architectures are symmetric in terms of encoder-decoder. And they decided that a decoder doesn't need a lot of convolution layers, so they make it much more slower. Or small. The next architecture was very extremely popular. It was introduced by Google in 2017. It's based on exception network. It applied depth-wise separable convolution. Depth-wise separable convolution consists of 2 steps, 2 layers. First, they are doing. Depth-wise convolution. Depth-wise means that you are not performing your convolution in all the depths of your channels. You just take one channel and doing your convolutions only by channels. And then on the second step, you apply one-by-one convolution. It was really, really popular. Everyone told about it. But I don't think it was good. Why? Because they don't have any comparison with Henet. Henet was developed for segmentation, and MobileNet was developed for classification. And they just maybe discarded or didn't know about. And thank you. Сколько времени? Сколько времени осталось? 20 minutes. So if we really count all this sum as multiplication at operations, we find that in most cases, Henet blocks are much more efficient than MobileNets. MobileNet architectures were improving, and in 2017 there was released the ShuffleNet architecture, and they highly exploited the idea of group convolutions. So they divide the tensor in 3 parts and doing convolutions independently for each of these 3 parts. It's at the first stage. But then they decided that independency is not a good thing, so they offered to mix parts from different groups. And so everything becomes more good. So it is the first MobileNet architecture. So one is modified. So 3x3 depth-wise convolution and 1x1. And they just add channel shuffle, and everything is going good. And one of the recent papers is MobileNet version 2. It introduced inverse residual block. So the standard idea is then you have the input tensor doing compression by input channels, and then apply special convolution, and then you expand it. And they also have a skip connection. But they reverted the idea. They have a low number of input channels, then they expand, doing convolutions, and then shrink back. And the next, a few words about it. I said it before. They showed some good result in paper, but it's too early to say that it's good architecture for real applications. The next architecture is quite new. It was released maybe in May. It's called Henet. It proposed 2 ideas. I like the idea that they combine 2 types of skip connections. They use both addition skip connection and concatenation skip connection. They try to use good from both worlds, as ResNet is known for addition skip connection, and DenseNet is known for concatenation. So they used both ideas and combined it in the architecture. And they proposed another idea for, they improved a little bit to the channel shuffle. They're just doing different number. So when we look at ShuffleNet, they every time divided the input tensors for 3 groups. But they has in their paper varying a number of groups in the block. And I think the most interesting and fascinating idea in the recent years is Shiftnet. They propose not to use standard convolution at all. They have 0 flops replacement for it. So how they do this replacement? They take the first channel and shift it a bit to one side. Then take another and shift it in the other direction. So everything shift a bit. So our network in our tendency is a bit shifted everywhere. And at the end, they are doing one by one efficient convolutions. So our net started to have a receptor field. But the problem with this technique is many frameworks don't have a good support for this idea. And some words about porting to your device. I told before that the best way for iOS is Caramel. Everything is working extremely good here. And when we move to Android, we face a lot of problems because most of frameworks are unready, mostly because of different bugs. And many approaches are not supported. For Android, the best frameworks at the moment are TensorFlow Mobile, and we are waiting for good TensorFlow Lite release. But there is some demos. For example, Facebook hardly use the framework called Cafe 2, developed specifically for mobile devices for Android. And for microcomputers, we can run all general frameworks, but I don't think that it's a good idea to, at the current moment, to use specialized frameworks for this. I think there is a wonderful thing called My Videos. It's a small USB chip. You can connect it straight to the Raspberry Pi. And it's a good GPU accelerator. And when I tried to run my Raspberry Pi with neural network, it was overheated. But when you plug in My Videos, your Raspberry Pi stays cool and everything is on My Videos. And it works extremely fast than trying to put efficient network straight to the Raspberry Pi. So that's all. Thanks for your attention.
I have a microphone, so I will handle questions. So just we're trying to fix last minute problem with next speaker. Who will be first? You? Okay.
Okay, thank you for your talk. My question is, which is the most efficient trick, one which you will highlight from your talk, how to have real-time nets for embedded?
I really like idea of one-by-one convolution compression. You can use factor 8 or 16. It really helps. Then I like the idea to put in this block just a special convolution. And I really like to work with skip connections. So if you add skip connection to your architecture, everything goes much, much better. And though it doesn't take a lot of operations.
Yes, so do you perform such techniques for this known nets and which results are?
Yes, I performed, I combined different ideas from all of these papers, but the results are close as it was working in the company.
Clear, thanks.
Okay, okay. Thank you for the talk. And I'd like to ask from the recent papers that you mentioned, which one performed best in your experience? Like 2008 ones you told.
I think it's Henet.
Okay, thank you.
Hi, thanks for the talk. And my question is about, you said that MobileNet version 2 is not very good for the real application. Could you tell us some arguments why?
I don't have good arguments at the moment. Most of the people I know think that it's just overfitted architecture for just small data sets.
So it was just overfitted in the paper, yeah, and that's why it overperformed? Or,
I don't really know.
Oh, I see. And another question, maybe you've tried to apply depth-wise to SqueezeNet? Have you an idea? Because they have a convolution, fully convolution layer in the beginning, and in every fire module they have 3x3 that could be maybe decreased by depth-wise.
It's a good idea, but I have experience with it, and maybe it's exploited. I didn't read yet the paper called Squeeze Next. Maybe it's connected idea with it.
You can take more. Okay, let's finish with this part.
Okay, thank you for the speech. Do you have experience with vendors? Neural network frameworks? I know that Qualcomm has its framework and Huawei. So the top chips now from these vendors. Do you have experience in conversion? How they works?
I had a bit of experience with Snapdragon framework, but when we tried to convert our network to their framework, it was not working. We tried to connect with support members of the Qualcomm, but there is no any documentation, so we just refused to use it. And the same thing was with ONNX. ONNX was released a year ago, and I worked hard to transfer network from PyTorch to, I don't remember, maybe to Keras, but there was also problems with documentation and etc. They had lots of bugs in the converter.
Are you okay with 3 more questions or 4 more questions? You ready to answer more questions? Okay, okay.
Did you make some researches on accuracy price? For example, how much accuracy we lose when using cont 1 by 1 by downsampling? Because when we use downsampling, we lose some information.
My personal study shows that mobile nets have usually better accuracy, but Henet loses much more accuracy, but it's extremely useful for real time.
And Mobius, this USB flash Mobius, can you say which frameworks does it support?
Or can you repeat your question?
At the last slide, you shown some USB device, Movideos. Which frameworks does it support?
It supports conversion from Keras. So they but I don't remember the other frameworks that we can convert from.
Yeah.
Thanks for speech. You mentioned that you did experiments with Movideos, and I would like to ask which one, like object detection, segmentation, and which FPS you achieved?
I tried only to run classification networks. So I don't think that I have a big experience in Movideos. I mostly have experience in FOCRML.
Okay, thanks.
Thank you for your speech, and I want to ask, did you try ONNX for porting and inference your models on low power devices?
No, I have no. I had experience to port from PyTorch to ONNX, then from ONNX to Café 2, but it wasn't working. At the moment, it was September of the last year.
Okay, thank you.
More questions? Okay, we are fine. Paul, thank you very much for your talk. Make applause for Paul.